Okay, this is a brief lesson on even and odd to explain what even and odd functions are better. And I will first go over the definition, and then there's two examples that are found in the practice problems for fundamental function mechanics. The first thing to talk about is what we mean by even and odd. And so with polynomials, this is actually kind of nice. And I'll get to a rule that is going to illuminate why we call it even, why we call it odd in the first place. But let's first start like this. So if you have a function, and let's call this function f of x. And suppose we know that the domain of this function is D. Okay, so f of x with domain. And remember that the domain of a function is simply what values x we're allowed to put into the function. So then we can call that a set. So D is the set of all of those x values that we're allowed to put into the function. Now, there's going to be two properties we're going to look at. Sometimes it is true. There are some functions in which if I took the function and I substituted negative x into the function, that is actually the same exact thing. It's going to give the same result as just f of x by itself. In other words, the negative side isn't going to change the value or the output of the function. So if this is true for all x in the domain, so here's a quick explanation of what this is. If you see this upside down capital A symbol, that is the English, and you can read that as for all. Or sometimes they say for each. So for each, for every, for all, basically for all values of x. And then this symbol right here is the word in. This is a slightly more common symbol. You might have seen that one before. So for all, or for every, for each value x that you can find in the domain of f, that's what this we call D, this is true. So we want this statement to be true. It can't be true just for a few particular instances. It can't be just, it works for a few of the values of x. It needs to be true for every single value of x. And this is going to be what we mean by an even function. Actually, I'll do this in a different color so I keep it separate from everything else. And this will be our even function. Now, visually, what this is going to mean is that this particular function is going to have symmetry. And this symmetry is going to be about the y-axis. So you can imagine having a function. We could use the quadratic. So this would be f of x is equal to x squared, for example. Now, if I were to kind of think about the y-axis here, and then spin it and kind of rotate this around, it would be perfectly symmetrical. In other words, rotating by the y-axis, and then flip it over, it's going to look exactly the same. It's a mirror image from this, and if I reflect it onto over here. So that's where we get symmetry from with even functions. It's going to be around the y-axis. So if you've got your function values coming up on the positive side, like positive x values, then it's going to spit out the same exact shape except for the mirror image over for the negative x values. And that's what this is communicating right here. Now, you'll notice something, that the exponent is an even number. So x squared is an even, that too is an even number, and we have an even function. So I will tell you this, that if you have a polynomial in which every single power of x is even, then it will be also an even function. That's kind of an easy way to go about it, which means we can automatically know that the functions like x to the fourth power. We could add x squared on there. Or if we had a different function, g of x, and this was x to the even, like, say the 10th power, a larger power, and some other things on here. These are even functions, and we know that because of these even powers. However, if you throw in an odd exponent, you break the pattern, you break it up. So you can't have something like x plus x squared, because the power on that x is a 1, and 1 is an odd number, which means that this is no longer going to be an even function. So this one would fail to be an even function, whereas these are even. So that's even functions, is they have the symmetry around the y-axis, because when you negate the x value, it's going to give the same function value. And then the trick for that is, if you have a polynomial, then just double check to see if all your powers are even, and then it'll be an even function. So I'll show why this is the case. Is that if we have a function, so let's make a function, and suppose it's going to be just x to the 2n. In other words, this is going to be an even power. So we'll have n is just an integer. And that's what this means again. So here's the in symbol again, and the double struck z is the integers, the set of integers. So 2 times an integer is going to give you an even number. Now, we're going to show that this is always going to be even. And the way we do that is we're going to first start with the left side of the equation here. We want to start by plugging in minus x, and then simplifying algebraically, see what we get. If we plug in minus x into here, well, we replace every instance where there's an x with a minus x. So minus x to the 2n. But the thing is, we know that this is just minus x to the n raised to the power of 2. And that's an algebraic as an exponential property. So when in the lesson that we talk about exponent laws, the product of 2 exponents is going to have an exponent to an exponent. Now, this square means that we're multiplying the number by itself. So we've got minus x to the n times minus x to the n. But we know that negative number times a negative number is going to give a positive number. So then minus 1 here and the minus 1 here are going to cancel, and what's going to be left is just positive x to the n squared. But again, if we simplify, that's just positive x to the 2n. And if you look what happens, well, x to the 2n, that's just the original function. And so this is always going to be true. We didn't choose a specific value of x to arbitrarily make this work. So we see that f minus x is always going to equal f of x. And that's true for all values x that are real numbers. So that's how we know that even exponents are going to yield even functions. The other kind of function we have is odd. And since this is in digital world and video lectures, if you didn't get everything written down, just rewind the video and press pause. Use the flexibility of this format to your advantage in your learning style. Okay, so we're going to talk about odd functions now. So odd functions is going to have, the setup is going to be similar. We're going to have a function f of x with domain D. And how we're going to do this is it's going to be considered odd is if we're going to plug in minus x again. So that's how we started. But instead of us having just returning the function, it's returning the function, but the negative version of the function. And this is what we're going to mean by odd function. So it's going to have a different kind of symmetry. A good example of this, and I should include here that this needs to be true for all x in D. That's important. And so a very common example of this is x, the cubic function. The cubic function is odd. cubic function looks something like this. So this would be f of x is equal to x cubed. And so notice that we kind of have symmetry. It's symmetry about two things. What you're going to first do is you reflect about the y-axis. And when you reflect about the y-axis first, you would get something that looks like this. But then after reflecting about the y-axis, then you want to reflect by the x-axis. You reflect by both. And what happens is then you flip it down and it's going to now be down here in blue. So you do two reflections. It's symmetry about the y and x axis that you are flipping. And that's visually what it means to be odd. And then analytically, it's going to be something similar. So just how the even functions had even exponents, now odd functions are going to have odd exponents. And you could show that just like we did in the previous situation. So this is what it means to be odd. This is an odd function. And the method that you would go about showing that x cubed is an odd function analytically, so here is the visual graphic way you could do it, and the analytical, in other words, algebraic way, is to say, okay, well, if I have f of x is equal to x cubed, then if I start by plugging in minus x, that's always the first step, what happens? So I'm going to replace minus x everywhere there's an x. In this case, I get minus x cubed. Okay, well, that means we have minus x times minus x times minus x. I know that the negative one here and the negative one here is going to cancel. And so I really have x squared times minus x. So a positive times a negative is going to be negative minus x cubed. Now, x cubed, though, is the original function. So I just have a minus sign out front. So really what I've shown is I got a minus sign out front and then the original function. F of minus x gives negative f of x. And that is the property of odd functions, because that's true for all of the x values. So now that we've talked about our even functions, what that definition really is, odd functions, we do want to make sure that we understand that sometimes a function does not necessarily have to be either even nor odd. So it doesn't have to be even, doesn't have to be odd. And so those functions, we just say they're neither, and we move on. And that's perfectly fine. So again, pause the video, write down the notes that you need to do before moving on, because now we're going to talk about the practice problems 9 and 10 from Fundamental Function Mechanics lesson. All right, so this, we have, I'll do purple this time. Okay, we got f of x, 3 times the square root of x. We want to determine if this is even, if this is odd, or neither. Now, we can first get a good a graphical intuition for this. And before I start, pause the video and see if you can first sketch out the graph and determine what you think. If we pause a moment and look at the graph, we're going to notice that 3 times the square root of x is going to look something like this. It's going to be 3 times that square root of x kind of deal. So this is f of x is 3 times the square root of x. Now, we ask ourselves this question: does this function have symmetry around the y-axis? Or maybe the y and the x-axis? Well, no. In this case, we don't actually have anything over here. So there's nothing being reflected over here at all. There's especially nothing down here being reflected. So that's not really the option. Now let's double check and see what our work is if we're going to show this more analytically. So f of x is 3 times the square root of x, which means that if we're going to substitute minus x, we have to put a minus x every single place where there is an x. And so that gives us the square root of minus x. Now, that square root of -1 is I. So this is going to be 3i, the square root of x. Well, this is most definitely not f of x. It's also most definitely not minus f of x, because now we've just introduced this imaginary component. So this is neither even nor odd. It doesn't satisfy either property, so we can just say it's neither and then move on. So that's question 9. Make sure that makes sense. Make sure that you could do that on your own. Double check it with your own work. Okay. And then the last question we'll do here, this is question practice problem 10. And let's do this one. I don't know. Let's do it in blue. Okay. So we got g of x, x to the 2/3 power, and then 2/3 x to the 4/5. So we have fractional exponents here, but that's okay. Even though we might not necessarily know what the graph looks like, I definitely couldn't just graph this for you from memory. But we can use analytical methods to determine whether it's going to be even, odd, or neither. And the first step, what is the function? Well, g is x to the 2/3 plus 2/3 x to the 4/5. And then we are going to plug in minus x into the function. That's the first step again. And then substitute minus x everywhere there's an x. So in this case, we're going to put a minus x here, 2/3, and then 2/3, and then here's where we would put that x. So minus x here, 4/5. Now, let's first understand, remember from the exponent rule. So I think it was the overlooked algebra lesson, is that if you have the numerator of these rational powers is kind of like the exponent, a regular exponent, whereas the fractional part is the root. So what we're really looking at is, if we rewrite it for visual simplicity's sake, we're looking at this. We're taking the cube root of minus x squared. And then where the cube root's coming from, that 3. So it's a fraction, so that's the root. And then the 2 is the numerator, which is why it's the exponent. And then we got 2/3 times the 5th root of minus x. I'll write that clear. Minus x to the 4th power. Again, the 5th root is because 5 is the denominator in the fractional exponent, and the 4 is exponentiated here because it is the numerator of this fractional exponent. Now, here we say, hold on, this 2 is even. This 4 is even. So that means that those negative numbers, a negative number multiplied by itself an even number of times, we already showed that that's actually going to be a positive result. I will get back so minus x squared is going to give me back x squared, and minus x to the 4th is going to give me x to the 4th. So I can rewrite this as the cube root of just regular x squared, plus 2/3 times the 5th root of just regular x to the 4th. And then rewriting back into the fractional exponents, we have x 2/3, where the numerator is coming from the power, the denominator is coming from the root, and then 2/3 x to the 4/5, where the 4 is coming from exponent here, the power, and then the denominator of is the 5, the root. Now, if we go back to the original function g of x, we notice that this is actually just exactly what g of x was. So this is g of x. So we have shown that g of minus x is equal to g of x. And this is true for every single possible value x. There was no consideration and specific value of x required. So that's true for all x in D. And in this case, the domain, we're allowed to put any real number. And that's what the double strict R is, the real number, set of real numbers. So the conclusion is even. So even though I don't know what this graph looks like, I know it must be symmetric about the y-axis because it is an even function. So that is even and odd functions. It's kind of how we do these, how we show something is even or odd or neither. And understanding these definitions and understanding kind of those shortcuts, especially with polynomials and exponents like we saw in this lesson.